Great. Okay, so thank you for doing your topic test for programming techniques. We're going to build on that by looking at different ways of programming, which means that we need to understand what a programming paradigm is. We're going to focus a little bit on high-level programming languages. We'll go through procedural and assembly, but we want to spend most of our time in this topic talking about object-oriented. So, programming paradigm is a way of programming, a way of thinking about programming, a way of conceptualizing problem solving using code in a more human-like way. So we're going to go through most of these. We're not going to cover functional programming for OCR, although I will point you to some resources that you can research if you're interested in this kind of stuff. We want to create a program procedurally, and then we're going to make the same program with low-level programming, and then we'll do the same program with object-oriented programming. We're probably not going to do functional today. So let's start with a really simple program. Let's make a console app in the W drive. Let's call it adder. I'm not even going to add it to a Git repository because it's going to be such a simple program. All I want it to do is ask the user for two numbers. Oops, I'm putting comments in the Pythonic way. Ask for two numbers. Add the numbers together. And display the result. So this is our input. This is our process. This is our output. And it's just going to go from top to bottom. There's no real thought about the structure of the code at the moment. It's just going to flow from top to bottom. So we've just done the first one for number one. There's lots of debate and disagreement amongst programmers as to the order that you write your code. What do I mean by that? Well, when I do console.write, I open and close the brackets first and then put the semicolon, because I'm going to be less likely to forget to balance the brackets afterwards. And then I go back and I put the arguments inside those brackets for enter number 2. It's perfectly valid to do it the other way around, to just write it from beginning to end. But the way that I think is the way that I code. My thinking paradigm is I want it to be as close to my programming paradigm as possible. So I don't always write from left to right. So int.parse, I want a number. What number do I want? I'm going to ask the question. Oops. That's my thinking paradigm. And I'm obviously thinking wrong because I want a different integer here. So always think carefully about the variable names that you've got here. I think sum or sum of two numbers or something like that would be a better choice than num3. But yeah, good. We've got the process here. Oops. So there we go. We're going to test this with 5 plus 6, and it's 11. Okay, great. So this isn't a particularly complicated program at the moment. It just goes from top to bottom. It's a good example of sequence, but it's not really procedural yet. It's high-level programming because we're not writing individual memory locations and really simple instructions. We're writing in a almost English way. So if we want to make this procedural, we're going to need some procedures or functions. So I would like to be able to do something like, let's just ignore that for now. I'd like to do add two numbers. And then I can do int sum equals add two numbers. Should I specify them as parameters, or should I just get that procedure to do it? Don't really know. So let's Alt Enter to get this to implement it. Come on, generate the method. Yes, please. There it is. Then all of this bit can go inside that function. We can then return a value. Return num1 plus num2. And we have code now that is a little bit easier to read. Because abstraction, we don't care how this works anymore. We just know that it's supposed to add two numbers. We should probably describe what it does. Ask the user to enter two numbers, add them together, and return the result. There are no parameters, but there is a return value. Integer value sum of two numbers. So when we say abstraction and we say ignoring the unnecessary detail, we don't mean that that detail is not important. It's very important. Abstraction just means hiding the unnecessary detail for that moment in time. It's still necessary, but in order to add the two numbers, we don't really care how it works. We just want it to do it. So this is now procedural. We've broken it down into procedures and functions. So let's plop that in here. And say that a procedural language allows us to use procedures and functions. Why? Well, we've talked about modular code already. It allows you to not repeat yourself. Remember that acronym DRY, don't repeat yourself. Why? Because if you repeat yourself, you're taking effort. Effort is time, and time is money. Also, if you repeat yourself, you're likely to make mistakes multiple times. So we've said here some advantages of procedural language code. It's procedural if you're using procedures and functions to break the code up to make it modular. Why is that useful? Because then you can then reuse it, saves time, effort and money. But also, if you choose the names of your subprograms well, wisely, sensibly, so that the names describe what it does, then your code is easier to understand. Because if you're looking at someone else's code and there's lots of procedures and functions, you just look at the functional procedure name and it describes what it does. So let's try and do the same program in assembly. We're going to use tank.withcode.uk and click on the tank. And let's see if we can do this. So don't worry if at this point you're just watching rather than doing. Comments are the same. I think you can have hashes. No, you can't. So double forward slashes. Let's write down our comments. Ask two numbers. Add them together. Display the result. Let's look at our instruction set. So, instructions for a low-level programming language are harder to understand. These are mnemonics. There was a question in the Year 11 exam, wasn't there, about mnemonics, which caught out quite a lot of people nationally for Edexcel. These are mnemonics, a couple of letters that stand for something. We want an input that reads a value from an input device and stores it in the accumulator. So let's just go imp. So it's not console.readline, it's just imp. Very short. One instruction is one memory location. So it's not a complicated compiler that optimizes the code. It's really simple to go from what the user writes to what actually appears in memory. So that's all we need really, but we need to input twice. But notice we can't do something like x equals imp or num1 equals imp. It doesn't understand that. We have to store it in these registers. What is a register? It's a very small storage location. We've only got one accumulator to accumulate stuff. And once we put something in it, we're going to overwrite it if we ask the question again. So if we actually run this program and step through it, fetch, decode, execute, it's going to ask us for a number. I put in 4. 4 is going to go into the accumulator. Hooray. Then we fetch the next instruction, 901. It goes into the instruction register. We'll decode it. 901 means input. And we'll execute it. I'm going to put 5 in. That 5 has just overwritten the value in the accumulator. So rather than overwriting it, we need to store it. So let's store it somewhere. I could say store it at memory location 99, which would work. I'll prove it. Let's see. Let's step. So we fetched the instruction. Where have we fetched it from? We fetched it from memory location 0. How did we know to do that? Well, because the program counter stores the address of the next instruction, and it stores a 0, so that's where we're getting our instruction from. What do we do with the instruction? We put it in the instruction register. There it is. Let's decode it. 901 means input. So when we execute it, we need to put a number in. Hooray, there it is. It's in the accumulator. Notice the program counter has incremented. It's gone up by 1. So the address of the next instruction is here. So let's fetch it. We've now fetched the 399 that was in memory location 1. We've put it in the instruction register. We'll decode it, and that says store it. Store it where? In memory location 99. Let's have a look at help. Let's have a look at memory location 99. It's currently zeros. But when I press step to execute it, the value that we typed in is now currently stored here. Okay, so we're storing data in memory. That's not very readable. What I'd like instead is to store this in num1. So I'd like a variable called num1. Well, how do I do that? I need a label called num1, which is going to store some data. There you go. We just made a variable. I'm going to need num2, which stores some data. Num3, no, sum, which stores some data. I've got 3 variables. Notice how each instruction takes up 1 memory location. Each data value takes up 1 memory location. So we're going to have to be really careful after we've done our code to stop. Otherwise, it's just going to go on and execute our data. So let's prove it. Let's restart. Let's write a virus, shall we? Let's step through, fetch, decode, execute, put in a number. What number shall I put in? I'm going to put in the number 901. Okay? 901 is in the accumulator. Let's fetch, decode, execute so that the number 901 is now stored at memory location num1. Can you see what's going to happen? Fetch, decode, execute. It's just going to ask us another number. I'll put 0 in this time. I'm not actually doing anything with that yet. I probably should. But when I fetch, decode, execute now, can you see we're fetching data? The CPU has no way of knowing that that is data. It's just a value. And it's going to try and execute that value, which is how a lot of viruses happen. The user has tricked the computer into storing a value which is then going to be executed by mistake later. So, bad idea. We don't want to do that. So we need to store the second number. So STA is the mnemonic. STA stands for store. We need to say where we're going to store it. We've already got a data location, so we just need to put store it at the memory location specified by this label, num2. Good. Now we need to add them together. So we've got a mnemonic called add. But what does add do? It says add the value stored at the memory address something to the value in the accumulator register. Well, at this point, the accumulator stores num2. So if I say add num1, num2 is already in the accumulator. I can add num1 to it, and the result gets stored back into the accumulator. So let's store the result into sum, although that's not strictly necessary. All we need to do now is display the result. So all we need to do is out. Out will display whatever is in the accumulator. You can specify, in tanks with code, you can specify which output device, but in normal little man computer, it's just out, which displays a number. One very important thing that we haven't got yet is just halt, which means stop fetching, decoding, and executing instructions so that we don't accidentally execute the data. So here we go. Hopefully this will work. Let's restart the CPU. Fetch, decode, execute. I'll put 1 in. Fetch, decode, execute. Hopefully 1 should now be stored in num1. Hooray. Fetch, decode, execute. It's going to ask us another question. I'll put 8 in. 8 is currently in the accumulator, but it's not in num2 yet. It will be when we store it. Fetch, decode, execute. Ooh, hooray, look, 1 and 8. They're both in the right place. Okay, fetch, decode, execute. Add the 2 of them together. We've got 9 in the accumulator. Lovely. Fetch, decode, execute. Store that result, which was in the accumulator, 9. Put it into sum. Hooray, there it is. Fetch, decode, execute. Oh, there it is. It's displayed a 9. It worked. Well, the whole point of this really is to prove that we've come a long way since low-level programming. In the olden days, you wouldn't even be able to write out mnemonics like this. You'd just punch holes in a piece of card You'd stack those pieces of cards. I've got like year 7 print cards, a stack of them here. If your cards go out of position, your sequence is wrong, your whole program's messed up. But the holes in the punch card dictate the binary values, which determine your mnemonics, which determines the memory locations, which determines what your program does. So you've got it easy. If you're coding in Visual Studio and you're thinking this is hard, it is hard, but it's not as hard as it used to be, because Visual Studio is making it a lot easier than it used to be, which is before my day of. So assembly language, we'll come back to it in a lot more detail. Don't worry if you're not understanding this yet. At the moment, I just want the concept. And the concept is, this is a low-level programming language. So we put a lot of things in here. It's a low-level programming language. That does not mean easy. Lots of people at GCSE think a low-level programming language is like Scratch for beginners. It's not. Scratch is a very high-level programming language. We talk about the level of abstraction. There is a low level of abstraction. We're not hiding any detail here because you've got complete control over what the processor does. But you know the Spider-Man quote, with great power comes great responsibility. You can do bad things with assembly and you can get things horribly wrong. Your code is hard to understand even when you're writing it. It's almost impenetrable when somebody else has written it. You can get stuff that is fast. You can get stuff that is memory efficient, but you can also write stuff that's really bloated and slow. Modern day compilers can probably generate better assembler than most human beings can write. So if you write high-level programming languages like C++, the C++ compiler will then generate your assembly language for you and then put that into object code, and we'll look at that in another topic. But this is a different programming paradigm, and a programming paradigm is just a way of programming. So next lesson, we're going to put all that in context and switch on to object-oriented programming, and then go through all of these concepts.